In section 5 of chapter 9, we're going to, again, it's going to appear like we're deviating from inverse functions. In reality, we're not. We're just doing a little bit of legwork so that we can continue with inverse functions further. But I don't want to just skip past this material and assume you know it, even though we've gone over it before in this class. I want to do a little bit of a refresher, and that refresher is over what is called exponential functions. I'm going to throw in just a tiny bit more vocabulary and also show you one thing that we did in the past that we're going to define a little bit more in this lesson. There are two types of exponential functions. There's exponential growth and there's exponential decay. They algebraically behave look very similar. Graphically, they also look very similar, but you need to be able to distinguish one from the other. So, exponential growth means that you're going to start with a function that is relatively flat, and as time goes on, it's going to go up faster and faster and faster and faster and faster and faster until it goes up so quickly that your brain does not contain the ability with which to understand how fast exponential functions grow. I'm not exaggerating that. Our brains were not designed to understand this level of mathematics. You will not comprehend how fast exponential functions grow. Exponential decay functions, on the other hand, they start really, really high, and they slow down, and they slow down at a decaying rate. So they slow down slower and slower and slower and slower and slower. Here are some algebraic examples of exponential growth and decay functions. Exponential growth functions might be something like 2 to the x, or 3 to the x, or 4 to the x, or 5 to the x, or 5 over 2 all to the x, or 1.7 to the x, or 3.8 to the x. Basically, the base of the exponential has to be bigger than 1. So if you wrote it as a decimal, it should be 1 point something or bigger. Exponential decay functions are going to be something like 1/2 raised to the x, or 1/3 raised to the x, or 4 over 5 raised to the x, or 7 over 11 raised to the x. The base of that exponential has to be smaller than 1. As a case in point, we will not be dealing with exponentials whose bases are negative. So decay functions have to be between 0 and 1, not including 0, not including 1. Exponential growth functions have to be between 1 and infinity, not including 1 and not including infinity. Here's what we are going to be working on today. I have a bunch of exponential functions written in the format that you are used to in terms of transformations left or right, up or down, stretched or compressed vertically, and flipped vertically. I am not going to ask you to use those descriptors anymore. I am only going to ask you to do two things. Tell me, just by looking at the equation, if it's growth or decay, and then graph it. So problem number 1, I have k of x equals 3 times 2 to the power of x plus 1 minus 6. I know because there's a plus 1 next to the x that we're going to move left 1. I know because I'm subtracting 6 at the very end, I'm going to subtract 6. I'm going to go down 6. So we're going to go left 1, down 6. That'll be where the center goes. 1, 2, 3, 4, 5, 6 is right here. For exponential functions, there is a horizontal asymptote that goes through that reference point. Unlike rational functions, you are not allowed to cross that horizontal asymptote. Rational functions, we kind of could in certain circumstances. This you cannot. Normally, if nothing special was going on, your first dot is just 1 above the x. But if there's a stretch or compression factor, you're going to multiply it by that value. That's a short way of saying whatever number's in the very, very front, right here, that 3, that's where your first dot's going to be. From your center, go up 1, 2, 3 in this case. That is your first coordinate. The second coordinate comes from going from your center, right 1, and you will go up or down the 3 times the base of the exponential. 3 times 2 is 6. So from my center, I'm going to go right 1, up 6. If you want to generate more dots, be my guest, but that's enough for me to recognize it's going to go flat and curve up. Therefore, this is a growth function. Problem number 2, I'm going to do a little differently. I'm going to state what kind of function it is before I graph it. Looking at the function L, the base of the exponential is a 1/3. 1/3 is smaller than 1. Therefore, I know it has to be decay. Now, in terms of the transformation, it's shifted right 2 and up 1. There's my center. There's a horizontal asymptote that goes through the center of this function. Therefore, it will never, ever touch that location. The first dot is going to be a 2 above the x. Now, here's where you're going to be left with a choice. You can choose either or, but one of them is going to get tougher as we move forward. First choice, we do what we did. Go right 1, and then you'll go up 2 times 1/3. Here's the issue with exponential decay functions. This will be a fraction. This will be hard to multiply by these two and get a really nice number. You're going to get 2/3. It's hard to graph. It works, but there's an alternative. If instead we go left 1, then we can multiply the 2 by the reciprocal of this, because that would bring it to the -1 power. The reciprocal of 1/3 is 3. 2 times 3 is 6. So I can go left 1 and up 1, 2, 3, 4, 5, 6. So I can have a second dot that's going to be at a bigger value. Bigger values are easier to graph than really, really small fractions. And decay started really tall and then ended super flat. The next two I'll go through a little bit quicker because now we've got the general gist of it. The base of the exponential is a 4. It's bigger than 1, therefore it has to be growth. It's x plus 3 for the exponent, so I'm going to go left 3, and then it's plus 5, which means I'm going to go up 1, 2, 3, 4, 5. There's my center. Here is my horizontal asymptote. The first dot, -1/2 times 4 is going to be -2. So from my center, I'm going to go down 2 and draw a dot. My next, oops, no, that's wrong. It's just going to be -1/2. I apologize. That was the second dot. The second dot, we go right 1, and we'll go down -1/2 times 4 is -2. There we go. That's better. Start flat, curve down. And then finally, the last function in purple, the function delta. The base is 0.25. 0.25 is smaller than 1. That means we are dealing with a decay function. We're going to go right 5 and down 1. 1, 2, 3, 4, 5, down 1, which is right here. Here is our horizontal asymptote. Normally we would just go up 1, but I'm going to go instead down 1/3. Right around here. I could go right 1 and down 1/3 times 1/4 is 1/12, but that's really, really small. Instead, I'm going to go to the left, and it'll be -1/3 times the reciprocal of 1/4, which is 4. -1/3 times 4 is going to be -4/3, or -1.3, which is roughly around here. So it's going to look like this. And there are the graphs of my 4 exponential functions.